Hello, friends. Nice to see you back after 2 weeks. So, today we continue a topic on joint distributions. It's part 2. So it turned out that there is gonna be a part 3 on this topic while I was making this lecture, because the topic is quite large and it contains a lot of interesting applications and useful applications. So let me first start. If you have some questions about the first part of this topic, some difficulties, maybe something was not clear, so let me briefly go through that lecture part 1.
I have a question on a review of the previous homework. We had no review.
I'm working on it. Sorry, I needed
Okay.
to have more time because yeah. So I hope that I will be able to upload this today. Most of the solutions I've already made, but still need to finish it. Basically, you need to understand the following. We just extend all the concepts that we used for one variable to the case of 2 or more variables. Of course, we are not working with 3 variables. It's too difficult kind of in terms of computation, but the idea is similar. So we define the probability mass function for discrete random vector. And this probability mass function is just the probability that 2 random variables simultaneously take 2 values, x1 and x2. It's like the intersection of 2 events that we discussed in the first lecture. Then we introduce the idea of joint cumulative distribution, which is also an intersection of 2 events. So one event that one random variable is less than or equal to the given number, and the other variable is also less than or equal to the given number. Why? Because with the help of the cumulative distribution function, we are able to introduce the continuous variables, and we do this in the same way as for the univariate case. We have a joint cumulative distribution function, joint density function introduced in this way. And the only thing here that when you are calculating these probabilities, you need to be careful that it's a bit more, let's say, computationally intense and difficult compared to the previous univariate case. So here, for example, when we calculate this joint probability of one variable being within the interval and another being within the interval, we need to do this kind of long calculation, not just one function minus another function, but it's rather like something is minus, something is plus. I hope that you've got the idea how it is calculated. And then with the help of a joint distribution function, we introduce the concepts of marginal probability functions. So basically, marginal probability is the univariate case when you have 2 variables and then you transform everything in the language of one variable, either x1 or x2. So marginal probability function is the usual univariate probability function derived from the joint distribution. That's it. And depending on the type of the variable, either it's discrete or continuous, you're either sum over all values of another variable, I mean some probabilities over the value of another variable, or you integrate them. And another important concept here is conditional probability. So we discussed the concept of conditional probability in the lecture number 4, and we apply the same idea for the joint distribution. So if I know something about variable x2, for example, then I'm able to build the probability distribution of a variable x1. Well, basically, these concepts of conditional probability, marginal probability are used as the fundamental things in the courses of statistics and econometrics, because, well, I started with this. Actually, the first slide was about it. When we are trying to establish some relationship between two variables, we are using exactly joint distributions, and that's why the concept of joint distribution now is going to be used through the whole sequence of these data analysis courses, let's say. So yes, here I showed you an example of a conditional probability, and I guess, yeah, so we finished with this. So 3 important objects: joint probability functions, either cumulative distribution or probability density or mass function, marginals, and conditional probabilities. So once again, are there any questions about it? So also regarding the home assignment, yes, I promised you to have a home assignment from Monday. I'm working on it, and so my plan is to finish this also today. So today, after the classes, I will finish both the solutions for the home assignment, or like not the home assignment, but that's individual assignment, and also I will post the home assignment number 9. Yeah, after I post the solutions, if there are any questions, just let me know, and I will try to discuss it with you. Okay, anything to clarify? Can we continue? Okay, so then let's continue the discussion on the joint distributions. So the first concept that we introduce here is the independency of random variables. Independency is also quite important thing, and why it is important? Because when we, for example, work with some statistical observations, when we want to collect the data in order to prove or disprove some hypothesis, we usually want the observations to be independent of each other, and that's why we need to formally define this independency to understand what is the requirement of this independency. So remember from the lecture 4 that we said two events to be independent when the probability of their intersection equals to the product of these probabilities, probability of A, probability of B. So this is the definition. So we say that two events are independent if this holds for any events A and B. So now, if you define, just let's translate this to the language of random variables. If you define an event A as this, x1, one random variable is less than or equal to small x1, and event B as this, sorry, it must be also x2, that's a typo. Yeah, so then we can obtain the following definition. So if x1 has a distribution function, so this is the marginal distribution function, capital F of x1, and x2 has its own marginal distribution function, capital F of x2, and both variables have joint distribution function, capital F of x1, x2. Then these variables are said to be independent if and only if this condition holds. Well, basically, that's exactly the same thing as we know about the independent events. Now, these events are defined as random variables, and random variables being less than or equal to a given number. If this holds, then we call two random variables independent. If they are not independent, then we call them dependent, obviously. So, well, this is just a way how we can transform the idea of independent events into the language of independent random variables. So I can write this joint cumulative distribution function as in the language of events. So this is the same as the intersection of these two events. Simultaneously, x1 is less than or equal to small x1 and x2 is less than or equal to x2. And then, using the language of events, I can write that this must be the product of these two probabilities, and each probability separately is just the marginal cumulative distribution function for each separate variable. So that's the more extended version of this definition, and I'm showing you that these two definitions are somehow connected. Well, also, if these variables are discrete, then they are independent only if their joint mass function equals to the product of marginal mass functions. So that's so basically you don't need to use cumulative distribution function to check the independency. You can use probability mass function for discrete variables, and you can guess that the same holds for the continuous variables. Instead of cumulative distribution function, you can use the density function for continuous random variables, and that's how you can check the independency of two events. And what is important here that this condition must hold for all pairs of real numbers x1 and x2. So if you are able to find at least one pair for which this or this equality does not hold, then two random variables are not independent. If for all pairs of x's we have this, then they are independent. So let's use the same example as we used in the previous lecture about the supermarket. We have the following joint distribution of two discrete variables. We have the following marginals, and now we can check whether these two variables are independent or not. So intuitively, they shouldn't be independent, right? Because the number of people at the first counter and the number of people at the second counter must be somehow connected. When you have more people here, you have less people here, because there are only how many? There are three clients in the supermarket. That's why, well, there is some dependency. So how formally we can check this? Let's take the joint probability, for example, of x1 being 0 and x2 being 0. So it's here, 1 over 9. So now we can separately take the marginal probabilities of x1 being 0. This one. This is the marginal probability of x1 being 0, 4 over 9. And this is the same marginal probability of x2 being 0, 4 over 9. And now we just check the condition. So the product of these two marginals is 16 over 81, which is not equal to 1 over 9 to the joint probability. So we found one pair of values for which the condition of independency does not hold. And since at least one pair gives us this, well, we can say that these two variables are dependent. Once again, intuitively, they must be dependent. Formally, they are also dependent because we proved that this equality does not hold. In the case of continuous random variables, we do the same. I guess we used this example in the previous lecture, so let me check. It was No, it was not here, but yeah, this example when we calculated the marginal probability density functions here. From this lecture, from the previous lecture, we know that this is the marginal density function for x1. So here was the derivation of this marginal. And we have the marginal density for x2. So now when we multiply them, so I am taking the marginal density of x1, marginal density of x2, which is 2x1 times 1, which is the same as the joint density. So that's why x1 and x2 are independent, because formally I found that the product of densities equals to the joint density. So I think that the independency is quite simple thing. You just need to know the joint density, you need to know the marginal densities, and then, or if it's a discrete variable, you need to know the probability mass function or CDFs, depending on what you have, and then just check whether this holds or not, this condition. Any questions about independency? Okay. So then let's move on. In the lecture number 7, we discussed with you the concept of expected value. Expected value of univariate case of one random variable. So now we will also introduce the ideas of expected values for the joint distributions and for several variables. So we will start with the following. Let y be some function of these k random variables. This is a general case. You can think about this as 2, 3, 4, 5, and so on. This is the function of the random variables. And then the expected value of y is, in the case of discrete random variables, with the joint probability mass function small p. The expected value is going to be, first of all, the product of this function values evaluated at different x's, values of x's, multiplied by the probability mass function, and then you need to sum over all x values of x1, all values of x2, and all values of xk. Let me remind you from lecture number 7, we used something similar for the univariate case. It was here. Look, we had y as the function of one random variable, and then we summed over all values of this x when the function evaluated at these values have been multiplied by the probability mass function, or in case of the continuous variable, we integrate over them. So now again we extended this to the general concept that we have more than one variable, and we have these k sums over all values of x1 and x2, x3, x4, and so on. So this is for the discrete case. If random variables are continuous, as you may guess, we just change the summation signs with the integrals. We integrate over the whole range of real numbers from minus infinity to plus infinity. And we multiply, instead of the mass function, we multiply this by the density function, joint density. And don't forget to put here dx's to complete the integral. So it might look ugly. So let's see the example how it works in practice in the case of two variables. So here we have discrete random variables. And we need to find, for example, the expectation of x1, x2. So the product of two random variables. So how should we do this? Basically, we need to take all combinations of x1 and x2, so 0, 0, 0, 1, 0, 2, and multiply them by the respective probabilities. Then 1, 0, 1, 1, 1, 2, multiply them by the respective probabilities, and then this. So we have 9 combinations of x1 and x2 multiplied by the respective probabilities. Something like this. Look, I'm taking first value of x1 and the first value of x2 at 0 and 0, and I multiply by the probability mass function evaluated at these pair of variables, 1 over 9. Then I take the other possible combination of random variables 0 and 1, multiplied by their probability. Then I have 0 and 2 multiplied by their probability, and so on. So in total I have 9 values. So luckily the calculation of this is quite simple because the first line is 0, right? So everywhere I have zeros as the terms. Here it's also 0. Here it's also 0. So from the second line I have only 2 over 9. And from the third line I have also zeros everywhere. So the expectation is 2 over 9. So kind of the calculation itself is quite simple. I jumped somewhere. Yeah. Oops. 7. Yeah. So the calculation is quite simple for this particular case, but kind of in practice it's ugly because you need to calculate all the combinations of the possible values of x1 and x2. And basically it makes us some nice illustration why do we want to substitute the discrete case with the continuous case. Look, even for this simple example, when you have kind of 3 by 3 matrix of the values of x1 and x2, the calculation of such thing as the expectation of x1 and x2 takes a lot of time. Well, if you don't have kind of software or something which helps you to calculate this fast, then it takes a lot of time, and maybe sometimes it's easier to substitute everything with the integrals, because in the case of integrals you don't need to sum kind of every number. So let's look how we can do the same for the continuous random variables. Back to this same example, we have a joint density 2x1 for values of x1 and x2 between 0 and 1. And we also need to find the expectation of x1 and x2. And in order to do this, we simply apply the same approach as for the univariate case. So I'm taking this function x1, x2, and I multiply this by the joint density function here, f of x1, x2. And I integrate over variable x1, and then I integrate over the variable x2. Well, now taking the particular joint density function, I know that both variables are changing between 0 and 1. And my joint density is 2x1. So here. Basically, you can choose which, because I hope you know that you can change the integration signs if these two are independent. So that's why you can choose which variable to integrate first, which variable to integrate second. So we start with x1. So basically x2 is just a constant. I put it here. And then I have 2x1 squared. And the integral of 2x1 squared is here, 2x1 cubed over 3. So evaluated is from 0 to 1, which gives me just 2 over 3, right? So then I have this integral of 2 over 3x2 integrated along x2. And finally, the integral of x2 is x2 squared over 2 evaluated from 0 to 1, and I have 1 over 3, which is the expectation of x1 multiplied by x2. So this is the way how I can do the calculation for the continuous random variables. Well, you can see that, well, if you are okay with integration, then the whole procedure is much simpler than this, because at least it's less computationally intensive, and you need to calculate less things compared to the discrete case. On the other hand, discrete case needs only arithmetics. For the continuous case, you also need to do some calculus, and you need to know how to deal with the integrals. So any questions about these two examples? Discrete case, continuous case. So let's move on. The expected value of a single variable. In the case of joint densities, that's the particular case of the previous material. So look, we can define a function of random variables as just one variable. For example, the function of x1 and x2 is just x1. So nothing can prevent us from this. Then look, then the expectation of x1 is going to be, in general, this is the integral, so double integral over x1 multiplied by the density function. And if I start integration, so if my inner integral is over the variable x2, so then I can take this x1 out of the integral sign, because this is the constant for me when I integrate over x2. And inside these square brackets, I will get the integral of my joint density function over x2. And let me show you something here. That's exactly the same object, right? So we integrate the joint density function over x2 and over the all values over the whole real numbers here. So this is nothing else but the marginal density function. And then this expectation is exactly the same thing as we have discussed in the univariate case here. But now I have an index 1 because I'm talking about a particular variable. Now it's x1 instead of this. So you see that everything kind of matches. And if I want to calculate the expected value of x1, I can either double integrate x1 multiplied by the joint density, or if I have the marginal density function, then I can simply calculate it in the same way as the usual case of an expected value. Well, yes, here is a comment that this integral in square brackets is the marginal density of x1, and finally the last expression represents us this univariate case. So let's see how it works, taking the two examples. So if you want for the discrete case to calculate expectation of x1 and expectation of x2 separately, so we have these marginals. And with the help of these marginals, we can simply calculate the expectation of x1. So x1 takes three values, 0, 1, and 2. Probability of 0 is 4 over 9. Probability of 1 is 4 over 9, and probability of 2 is 1 over 9, right? So I do this, 0 times 4 over 9, 1 times 4 over 9, 2 times 1 over 9, which gives me 6 over 9, right? And this is 2 over 3. And the same, exactly the same expression for the expectation of x2. Because the probabilities are similar and the possible range of the values of x2 is also similar. So the discrete case, for the continuous case, the same joint density. To calculate expectation of x1, we can do this. We can double integrate x1 multiplied by the joint density to x1. So first of all, I integrate over x1. So the integral of 2x1 squared is 2 over 3 x1 cubed. Evaluating this from 1 to 0 gives me 2 over 3. Then I have this integral 2 over 3 dx2. And when I evaluate this, when I find the integral, it's just 2 over 3 x2. Evaluate from 1 to 0 gives me 2 over 3. So this is the expectation of x1, 2 over 3. And the expectation of x2, so I change only one thing here, x1, I change with x2 because I evaluate this now. And when I integrate first over x1, it gives me x2 times x1 squared, evaluated from 1 to 0, so it's basically 1. Then the integral of x2 is simply x2 squared over 2, must be index 2. And finally it's 1 over 2 here. And well, speaking about this example, that's the same as we can receive using the univariate case. Look, from the previous lecture, we know that the marginal density of f of x1 is this, 2x1. So I know how to calculate the expected value of one random variable. So I can apply this here. And this is the integral of x1. So it's not double integral now. It's just an integral over x1. And here 2x1 means this. Here 2x1 means just the marginal density of x1. So they match with the joint density. And you see how simple it is. It's much simpler than kind of doing this double integration. But finally, the result is the same. And for the second variable, my marginal density is just 1. So it was obtained here in the previous lecture. And when I integrate x2 times 1 over x2, it gives me x2 squared over 2, which is 1 over 2. So the same, exactly the same outcome as after this double integration. Okay, so now some properties of the expected values, and these properties are very similar to what we had in the lecture number 7. So here, just let me remind you briefly that if we have a and b some constant and x, y some random variables, then we spoke that expectation of a constant is just constant, expectation of a random variable plus constant is this, expectation of a product of a constant and the random variable is this product of a constant times the expectation, and the expectation of a sum of two random variables is the sum of their expectations. Right, so we must be familiar to this from lecture number 7. So now when we extend this to the case of to the multivariate case, we have something similar. So let's C be constant and g of x1, x2 be the function of the random variables x1 and x2. Then the expectation of a constant is a constant, exactly the same as the first property. So the expectation of a constant multiplied by a function of two random variables. It's number 3. And look, this x is just a particular case of this g of x1, x2. Because as I said, one random variable is a function of two random variables, like some special case of this function g of x1, x2 equals x1. So when we have an expectation of a sum of several, so k functions of these two random variables, this is simply the sum of their expectations. Well, this is the general case of a property number 4 here, and property number 2 basically, because like they both involve this summation. And knowing, for example, property 4 and property 1, I can easily derive property 2 as the particular case, right? So expectation of A is simply A. And now this is a general case. This is the general case for those properties. And one additional property is that if two variables x1 and x2 are independent random variables, and we have functions g of x1 and h of x2, so those are two different functions, and they are functions of only x1 and x2 respectively, then we have the following property. Then the expectation of their product, of the product of these two functions, equals to the product of the expectations. But look, this holds only for the case of independent random variables. And quite important thing that, well, if they are independent, then this holds. But the reverse is not true. If this holds, it doesn't mean that variables are independent. Because look, the condition of independency was introduced in the beginning. And we know that the condition of independency involves the product of either distribution functions or probability, density or mass functions. So we are able to call two variables being independent only if the product of their probability functions or density functions are equal to the joint function. Here is the consequence of two variables being independent. So if two variables are independent, then this property holds. But the reverse, once again, the reverse is not true. When you are able to establish this condition, it does not mean that two variables are truly independent. They might be dependent, even though this holds. That's an important thing, and sometimes so trust me, it provides a lot of confusion when we work with statistics or econometrics. Any questions about these properties? Okay, good. So let's then introduce the following. If two variables are not independent, we would like to measure their dependency somehow. So if they are not independent, we want to know how, let's say, how much are they dependent. And in order to measure this dependence of two random variables, we use the most popular measures. So one is the covariance between two random variables, and another one is the correlation coefficient. So here is the definition of a covariance. If x1 and x2 are random variables, they have expected values or means mu1 and mu2. So don't forget, we introduced this notation also here in the lecture number 7. We introduced that the expected value sometimes is just, for simplicity, is denoted with mu. And here exactly I denote this because if I would write expectation of x1, it would be very kind of heavy notation. So that's why it's simpler to write down this mean or expected values mu1 and mu2. So then we define the covariance in this way. So this is the expectation of the following product. So x1 minus mu1 times x2 minus mu2. Well, what does the covariance say about the dependency of two variables? So the larger the absolute value of the covariance of x1 and x2, the greater the linear dependence between them. So I highlighted this linear dependence because the covariance is able to capture only the linear dependence between two variables. If two variables are dependent, but they are not linearly dependent, the covariance will show you nothing, which is a problem. So the positive values of covariance indicate that x1 increases as x2 increases. Negative values indicate that x1 decreases as x2 increases. So basically, with the help of covariance, we are able to establish the direction of dependency between two random variables. Either they go up or go down. When one goes up, another goes down, or when one goes up, another also goes up. So a zero value of the covariance indicates that the variables are uncorrelated and that there is no linear dependence between x1 and x2. Once again, this is crucial thing. Zero covariance does not say that two variables are independent. Zero covariance means that two variables are not linearly dependent. They might be dependent, but the covariance is going to be zero or close to zero. So here are some graphical examples of dependent random variables. When we have x1 and x2 and when they are purely independent, so we might observe graphically something like this. So the distribution of their values is going to be kind of chaotic and you will not see any particular pattern. So this is for two independent random variables, x1 and x2. So here we have a dependent random variables with the weak dependency between them. So it's a correlation coefficient. So I will introduce the correlation later with a correlation of 0.3. So you see that they are somehow formed into in this let's say direction. So on average, let's say when x3 is greater than x4 is also kind of increases. So here we have a strong negative dependence between two variables, linear dependence, because it goes in this direction, and you see that well, when x1 increases, x2, like it's x5 and x6, okay, x5 increases, x6 tends to decrease. So this is the strong negative dependency between them. And here is a strong linear dependency, the strongest possible, because now you see that there is a linear dependency, and when x7 increases, x8 increases with certainty. This is just a linear case. So like here are two extremes. This is completely independent random variables. This is a dependent random variables, and these two random variables have the highest possible covariance and the correlation coefficient as well. And usually when we work with some data, when we work with some observations, we have something in between, like this or this, strong or weak dependency of two variables. But this is just a graphical illustration, and we are going to use similar graphs later on during the statistics course. So another way to calculate covariance is the following. So we can calculate covariance as the following difference. So it's an expectation of x1, x2 minus the product of the expectations. So this is an expectation of x1 multiplied by the expectation of x2. And you may find this similar to the following. So first of all, we know something which is called the variance. It's not covariance, it's just a variance. And look, we defined the variance as an expectation of x minus ex squared. Look, if, for example, x1 and x2 is the same variable, then you will get exactly this. That's the first, let's say, similarity. And then regarding this, we know that variance sometimes is calculated in this way. And once again, so if x1 and x2 are the same variables, it's going to be expectation of x squared minus the squared expectation of x, exactly like here. So, which means that the variance is the particular case of a covariance. Variance is a particular case when two random variables coincide, when instead of two random variables we have only one. So why this is true? So how to prove this? Here it is. So we have the definition of a covariance. Now I open the brackets, and when I open the brackets, I have x1, x2 minus x1 mu2 minus x2 mu1 plus mu1 mu2. Okay, so now using the properties of expectations, which we introduced here, I can use the property number 3 when the expectation of the sum equals to the sum of expectations. Right, so it's here. Instead of the expectation of a sum, I factor this into the sum of expectations. And finally, I have this. So look, if it's an expectation of x1, which is mu1, mu2, this is mu2, mu1, and this is mu1, mu2 once again. So I have minus mu1, mu2, minus mu1, mu2, plus mu1, mu2. And finally, two of them cancel out, and I have this. Very simple way how I can prove that this and this are equivalent. But the latter case is usually more simple to calculate. That's why we need to know what is the covariance in general. But usually, as for the variance, we used this formula because it's just simpler to calculate. For the covariance, we also will use this formula in most of the cases because it's just simpler and it's less computationally intensive. So let's see how we can calculate the covariance in the case of discrete random variables and in the case of continuous random variables. So what we know? We know that expectation of x1, x2 is 2 over 9, expectation of x1 is 2 over 3, expectation of x2 is also 2 over 3. Well, we want to find the covariance of x1, x2. So the first way, the direct way to calculate covariance is this. Look, it looks terrible because there is too much of calculations, and now you cannot just cheat and say, well, there are zeros somewhere. You really need to calculate all these things. Look, the logic is very simple. The logic is such that I'm taking each pair of x1 and x2, those are 9 pairs, right? And for each pair, I'm doing the following. So I take x1, 0, minus expectation of x1, minus 2 over 3. Then I take x2, 0, minus the expectation of x2, 2 over 3. And I multiply by the probability, 1 over 9. Then I do for the next pair, like x1, 0, x2, 1. So 0 minus 2 over 3, 1 minus 2 over 3, multiplied by their joint probability, 2 over 9. Then I do x1, 0, x2, 2, it's here, times 1 over 9. And then I repeat doing this again and again for all the combinations of x1 and x2. So those are 9 combinations. And finally, after all these heavy computations, because I can simplify only this, because the probability is 0, this and this. All the other things I really need to calculate. After all these long and terrible calculations, I have minus 2 over 9. Or I can use the other formula just to say, well, covariance of x1 and x2 is this expectation. Well, you remember that this expectation was also somehow long in the calculation, but we found a way to simplify because a lot of zeros. Well, it's just 2 over 9 minus 2 over 3 times 2 over 3, which is 2 over 9 minus 4 over 9, and finally it gives me minus 2 over 9. Much faster and much simpler. What does this 2 over 9 mean? So first of all, minus means that x1 and x2 are negatively related or negatively dependent. And once again, it makes sense because the nature of x1 and x2, so let me remind you what is the nature of these two variables. So x1 is the number of customers at the counter 1, x2 is the number of customers at the counter 2. And since we have only 3 customers, we have 2 customers and 3 counters. So definitely when there are more people at the first counter, there are less people at the second counter, and so on. That's why we have this minus. When more people go to the first counter, then definitely less people go to the second counter. But it's not perfectly related because we have also third counter. So that's why we don't know exactly, maybe if there are more people on the first, maybe if there are less people at the first counter, there are also less people at the second counter because all people went to the third one. That's why this number is not very large. On the other hand, we don't know large. What does this mean, large covariance? How much it must be? But we will discuss this issue a bit later. So now let's look at the other example of the continuous random variables and their covariance. So this joint density is taken from the example of this, so gasoline stock. So I hope if you don't remember, so let's remind ourselves this example. We had the tank of a gasoline, some reservoir, and we had 2 random variables. So one random variable x1 is a proportion of the capacity of this tank that is filled with the gasoline, and x2 is the sales of gasoline during the week. So these 2 variables must be related to each other because x2 cannot exceed x1. We cannot sell more than we have. And in this example, we had exactly this joint density. And what is important here that x2 it never exceeds x1. And x1, the range of x1 is from 0 to 1 because it's proportion, right? So this density function, they must be related and they must be dependent. So if you want to find the covariance of x1 and x2, so as we have seen in the previous example, the easiest way to do this is to calculate expectations separately and then to calculate the expectation of x1, x2. So the expectation of x1, we double integrate x1 times the joint density. So be careful, please, here. So x2 changes from 0 to x1. Here. The integral is not from 0 to 1, it's from 0 to x1. And when I integrate over x2, which gives me 3x1 squared here, then when I integrate with respect to x2, it's going to be x1 times x1 right here. So it's 3x1 cubed. And then I integrate this 3x1 cubed, I have 3 over 4 x1 fourth. When I evaluate this from 1 to 0, it's 3 over 4. So the expected capacity of this tank at the beginning of the week is 3 over 4, or 75% of the tank is filled. It's an expected value. So then the expected value of x2, so it's a bit more complicated calculation. Once again, we integrate with respect to x2. So 3x1 is just a constant here. So x2 squared over 2, evaluated from x1 to 0. So it's just x1 squared over 2, 3x1 squared over 2 gives me 3x cubed squared. And then I integrate this with respect to x1. It's 3 over 8 x1 to the power of 4. And then finally it's 3 over 8. So I expect to have 3/4 of the tank in the beginning of the week. And I expect to sell 3/8 during the week. And the expectation of the product of x1 and x2 is the following. So it's just x1, x2 multiplied by the joint density, and then I integrate first with respect to x2 here. So 3x1 squared is constant. The integral of x2 is x2 squared over 2, evaluated from x1 to 0. Sorry, it's a typo, it must be x, not y. You might be wondering where this y came from. Yeah, so it must be 3x1 squared, and here it's going to be x1 squared over 2, which is 3 over 2 x1 fourth. Then when I integrate this, I have 3 over 10 x1 to the power of 5, evaluated from 1 to 0, which is 3 over 10. So finally, I have all the necessary elements to calculate the covariance, and my covariance is 3 over 10 minus 3 over 4 times 3 over 8, which is this, which is 0.02. Yeah, so I didn't put this example on slides, but actually we can also do the calculation of covariance for this example. So here, if you remember, we proved that these two variables are independent. Right? x1 and x2 are independent. These variables with the following joint density. What if we calculate the covariance of these two variables? So we know this expectation of x1, x2, which is 1 over 3. So remember this number, 1 over 3. And we know the expectations of x1 and x2 separately. It's 2 over 3 and 1 over 2. So multiply 2 over 3 by 1 over 2 to get 1 over 3. And then that expectation of x1, x2 minus product of these expectations gives us 0. So for two independent random variables, covariance is 0. Exactly as we had exactly as we had here, right? So expectation of a product of two variables equals to the product of their expectations. That's why the covariance is 0. So now, what is the problem with the covariance? The most important problem, it is difficult to use the covariance as an absolute measure of dependence. Why? We don't know the strength of this dependency using covariance. We don't know whether this 0.02 is large or small number relative to the values of these random variables. We can say nothing about it. So that's why, so the value of covariance depends on the scale of measurements. We really want to standardize the value of covariance to say, well, this is the large dependency or strong dependency, this is the weak dependency. And we do this with the help of the correlation coefficient. When we standardize the covariance, we derive something which is called the correlation coefficient. So the definition is the following. If we have two random variables, x1, x2, they have variances sigma 1 squared and sigma 2 squared, and they have a covariance x1, x2, then the correlation coefficient between x1 and x2 is defined as following. So this is the fraction of covariance over the product of standard deviations. And standard deviation is the square root of variance. Basically, here in the denominator, we have the square root of a product of two variances. And it holds always that the correlation coefficient is between -1 and 1. When -1 is the strongest possible linear dependency, negative linear dependency, and 1 is the strongest possible positive linear dependency. When the correlation coefficient is 0, it means that the covariance is 0. That's the only possible situation when the correlation might be 0. And if correlation is 0, then it means that two variables are not linearly dependent. Once again, it doesn't mean that they're independent at all, but they are at least linearly not dependent. So I wasn't able to provide you an example with the correlation coefficient, so let's try to calculate this together. So we know the covariance for this case. Let's try to calculate variances of x1 and x2 and calculate the correlation coefficient for this discrete case, and then we will do the same for the continuous case. So what do we need to have for the discrete case? We need to know the variance of each variable. We need to know the variance of x1. And I hope you must remember from the lecture 7 that one way to calculate the variance is the following, right? So it's ex squared minus ex the second power. I think this way is the easiest way to calculate the variance. Once again, another way is this one, but this is a bit longer. Well, we have three variables. Basically, there is no difference. So let's use either of these ways. So let me show you both just to refresh our memories. So I am taking values of x1, it's 0, 1, and 2. And the expectation of x1 is 2 over 3. So 0 minus 2 over 3 squared multiplied by the marginal density of x1, which is 4 over 9, right? So the sum of these three lines, 4 over 9, plus then I take this deviation from 1, and here also 4 over 9, and then I take this deviation from 2 squared minus 1 over 9. So that's one way to calculate variance. So what do we have? We have 4 over 9 times 4 over 9 here, right? Which is 16 over 81. Plus, here I have 1, so 3/3 minus 2/3, which is 1 over 3, right? 1 over 3 squared, 1 over 9, it's 4 over 81. So it must be 16 over 81, right? This one. And here I have 2 minus 3, it's 6 minus 2, which is 4 over 3. No, wait, it's not 8. Yeah, 4 over 3, so 16 over 9 must be also 16 over 81. I hope it's correct. If not, check after me, please. So 16 plus 4, it's 20, 20 plus 16, it's 36 over 81. Okay, so that's one way to calculate the variance of x1 based on the joint distribution. So another way how I am able to calculate the variance of x1 is to calculate the squared expectation. So meaning that it's 0 squared multiplied by the marginal probability of x1, which is 4 over 9, plus 1 squared, once again multiplied by 4 over 9, plus 2 squared multiplied by 1 over 9. So this is the expectation of, okay, so let me do this step by step. This is the expectation of x squared. So here is 0, here is 4 over 9, and here is also 4 over 9. So in total I have 8 over 9. And now variance of x1 can be calculated as this 8 over 9 minus the squared expectation of x1, which is 2 over 3 squared. Right, so it's 8 over 9 minus 4 over 9, which gives me 4 over 9. Yeah, I think that we are able to simplify this also. So yeah, when we divide 36 and 81 by 9, we have exactly 4 over 9. So you see that both ways are possible. So, and since we have the same marginal distribution for x2, basically no need to calculate variance of x2, they are the same. So the variance of x2 is the same, 4 over 9. So all the numbers are similar. So what is the correlation coefficient for these two variables? So rho, the correlation coefficient is the fraction of covariance, and covariance is this, minus 2 over 9, minus 2 over 9, divided by the square root of the product of two variances. So it's 4 over 9 multiplied by 4/9. So we have -2/9 multiplied. So the square root of 4/9 times 4/9 is simply 4/9. When I divide by this, it's the same as multiplication by 9/4. And then finally I have 1/2 or -0.5. So that's the correlation coefficient. The additional thing that we need to do, that we need to know, is the calculation of variances. That's basically it. Questions? Okay. So then let's do the same for the continuous case. So for the continuous case, we also need to calculate the variances first. And let me calculate the variances with the help of expectations, because like calculating this in the continuous case, it's not a nightmare, but it might be kind of problematic. So we take the integral over, well, yeah, we need to take the double integral. So the first integral goes from 0 to 1, and that's going to be the integral for the first variable, dx1, right? So that's going to be the outside integral. And the inside, we will have the following. Inside, we will have the integral from 0 to x1 here. And look, now when I calculate this x1 squared, so basically I employ the same property as we introduced here. So I define a function of x1 and x2 as x1 squared. Right? And then I multiply this as x1 squared by do we have marginals for this from the previous lecture? I don't remember. No, we calculate marginals for another distribution. Okay. Yeah, so then simply need to follow this. So then it's 3x1 and dx2. Okay, so that's what I need to integrate in order to calculate this expectation of x1 squared. So what do we have here? First of all, let's try to simplify. X1 squared times 3x1 gives me what? Gives me 3x1 cubed. When I integrate with respect to x2, this 3x1 cubed is the constant, right? So I can leave it like this, or I can do something even more interesting. So I can take this out of the integral sign, like this. Okay, and so inside I have the integral of 1 with respect to the x2, which is what? Which is simply x2. Right, so I have now this x2, which must be evaluated from 0 to, must be evaluated from 0 to x1. And when I plug this here, it's just x1, right? So I have finally this 3x1 to the power of 4 dx1. And the integral of this thing is what? It's 3 over 5 x1 to the power of 5 from 0 to 1. And it's simply 3 over 5. Okay, so this is the expectation of x1 squared. And it gives me a chance to calculate the variance of x1 squared. Of f1, sorry, variance of x1 is what? So it's 3 over 5 minus, it must be the expectation of x1, 3 over 4 squared. 3 over 4 squared. So 3 over 5 minus 9 over 16. 80 here. 3 times 6, it's 18, right? So it's 48 minus 45. So finally I have something like 3 over 80. That's a variance of x1. So I do the same for x2, expectation of x2 squared. I can copy this integral and change only one thing here. Instead of x1 squared, now I have x2 squared, like this. So 3x1 goes out. It's not a variable, it's a constant with respect to x2. So I have x2 squared. The integral of x2 squared is what? So it's x cubed over 3. So it's x2 cubed over 3. No, I don't want it like this. Like this, and evaluated must be evaluated from 0 to x1. Okay, so now we have this, and this is what? This is the integral of 3x1 multiplied by x1 cubed over 3. Like this. So 3 and 3 cancels, and finally I have the integral of x1 to the power of 4. 1 to the power of 4. And this is simply 1 over 5, right? Finally, when it's gonna be x to the power of 5 over 5, evaluated from 1 to 0, so obviously it's 1 over 5. So variance of x2 is 1 over 5 minus the expectation of x2 squared, which is 3 over 8 squared. 3 over 8 squared. And this is 1 over 5 minus 9 over 64. Okay, so the denominator is gonna be 320, I guess. Let me check. 5 times 64, 320. Now here we have 64 minus 45, right? And 64 minus 45, it's 19 over 320. So this is the variance of x2. And the last step is to calculate the correlation coefficient. This is, what was the covariance? So the covariance was 0.02. Here the square root of this product, 3 over 80, which is 0.0375. So 19 over 320, it's 0.059375. So this multiplied by this 0.059375. So what do we have finally? 0.0375. Then we have a square root. Then we divide. And then 0.02. So it's 0.42. Okay, so we have almost kind of not that strong, but positive relationship between these two variables. And this makes sense. So the more you have in the beginning of the week, the more you are able to sell during the week. Okay, so that was kind of a live demonstration of all these calculations. Well, it's a bit terrible now. It's computationally heavy. I promise you that in the next semester we are going to use mostly some software to calculate this for us as well. But now we need to know how to do this with hands, just to understand the whole mechanics of all these calculations. And also check me if I had some mistake. Maybe I did. Surely we can compare this with the answers from the book. They must have these answers somewhere here. I think. Not sure, maybe not. Yeah, so they have this covariance. No, it's not this. That's, yeah, this is density function. So the covariance is here. So regarding the variance, regarding the correlation coefficient, didn't have it. Okay, so then let's believe that we were correct. Questions, guys? So we have established really important thing now about the correlation and covariance. In the next lecture, I will show you how we use this in finance, for example, when we combine different stocks in order to reduce the uncertainty about the portfolio. So I will show you this application, and also in the next lecture I plan to discuss with you something which is called order statistics, how to predict that and how to apply this to the case of auctions. What is the probability that your bet in the auction is going to be the highest bet among the other, let's say. So we will see some particular examples, because now we have at least some necessary background to work with some real cases, not just coin toss or throw in a die or something like this. Questions? We will have an exercise session on Saturday. We will try to calculate all the similar things, covariances, correlation coefficients, check the independency of two random variables, and then after that exercise session you will have the next home assignment. I hope to make it as fast as possible. Let's see that now the things are getting more and more complicated. That's why it takes longer and longer. So if there are no questions, then thanks for your attention. See you in 15 minutes for microeconomics.